Okay, so welcome to this video on the matching problem, which is another very famous problem in probability, the matching problem. And it's a problem that came fundamentally from gambling, and the setup is that you have a stack of cards. Now, in the conventional, if you've ever played Irish Snap, it's a similar game to that. Basically, what you would do is you get your cards out and you would go through them. Well, in Irish Snap, it's a one-player game. The matching problem is based on. So basically, you have a contestant and someone actually, doing the game. And the person doing the game is going to turn over the cards one by one and stack them on top of each other. Or rather, maybe it's the different way around, but it doesn't matter. And the other person is basically going to say 1, 2, 3, 4, etc. And basically, if you get a match, if you turn over the card which has a 1 on, say an ace, it would have been in classical card games, and when the person says 1, then they win some money. And if they go through the entire stack and then don't have any matches, so they don't say the right letter when the number comes out, and of course they have to say it in order. They have to go 1, 2, 3, 4. They can't. It's not quite that. It's not quite a game where you have to guess what number's coming. It's just basically all you're asking is you shuffle the cards and you will win some money if when I've shuffled these cards. There is a match, basically, i.e. the nth card is an n. So to make the problem simpler, we're just going to imagine that the cards just have numbers on them. So you have card 1, card 2, card 3, all the way up to card n. And then you shuffle them up, and basically we are going to ask, what is the probability that you have a match? What is the probability that somewhere in that deck of cards the kth card is in the kth position? So that's the matching problem. So we have n cards, and basically what we are doing is there are n positions, so 1, 2, 3, the cards are stacked on top of each other. So this is a card, this is a card, this is a card, and these are the positions. So I shouldn't have them on the letters in the card. So this is card in position 1, this is card in position 2, all the way down, and you've got n cards. So this is card at the bottom, which is the nth position, and each of these cards has a number on them. So for instance, this card might have number 5 on it, this card might have number 4, this card might just have number 3, and we're asking what is the probability that in the entire deck of cards there is at least one match. So basically, our sample space in this problem is every possible scenario that can happen. So this is our sample space. Basically, every possible scenario that can happen is you shuffle these cards, and every possible arrangement of the cards that can happen is an outcome of the experiment. So how many outcomes are there in the sample space? That's a good question. Well, I could have n different cards here, big N, then I could have n minus 1 different cards here, etc., all the way down. So there are n factorial different outcomes, and we're sticking all of those outcomes into this sample space. Now, of those outcomes, we have an event, which is the event that, for instance, card 1 is in position 1, is in position 1. So I'll call that event 1. Here we are. Then we have event 2, which is that card 2 is in position 2. You getting the idea? Card 2 is in position 2. So these are subsets of the outcomes. So there are loads of different outcomes that where there are loads of different outcomes that all satisfy the condition that 2 is in the second position. So all of those are in set 2, and of course there's a little bit of an intersection here with set E1, because there will be some outcomes where 1 is here and 2 is here, therefore they meet both. They're in both of these events. And we can go on, and we can add on every single, and then it gets messy once you start adding more of them. But basically we can have up to event n, where the nth event is, so E little n is the event that the card with little n on it is in the nth position, and we're asking what is the probability of E1 union E2 union all the way up to union E big N. So what is the probability that you have one matching? If you have one matching, you are in one of these sets, therefore you are in this union. So if we find out what the probability of this union is, we're done. So now we just use the inclusion-exclusion principle, which was the topic of the previous video. So this we can write as the sum of I is equal to 1 to big N of the probability of EI plus, minus the sum of I is less than J of the probability of EI intersection EJ, and etc. all the way down to plus minus 1 to the N plus 1 the probability of E1 intersection E2 intersection E3 intersection all the way up to intersection E big N. So now we need to figure out what is the probability that E1 happens. What is the probability of E1? So what is the probability function attached to E1? Well, here we need to ask what we'd need is we need to know what the ascribed value to this is, and the probability that you are in event 1 is equal to, we can say there are n possible outcomes. So this is actually a simpler. This is actually one of these simple problems where as I was discussing at length in the last video, each of the singletons is actually an event. And you can ascribe a probability to it, which is not the case for some probability spaces. It's not the case for a general probability space, but because we've got a finite number of outcomes in this probability space, then every possible outcome is itself an event and therefore has a probability attached to it. And in fact, all of the outcomes we are assuming are equally likely. So the probability of a singleton, so if X is a single outcome, i.e. it's a specific arrangement of the cards, then the probability of the singleton set containing X is equal to 1 over n factorial. So all we need to know, and that's for whatever outcome X is, so X is any element of the sample space. So if we want to know what the probability of this set E1 is, all we need to know is how many singletons we have in, and then we just use the fact that we're taking the union of a disjoint sets, and then we just apply axiom 2 of the probability space. So probability is hugely simplified when all the singletons are elements of the set of events. So if we want to work out the probability of E1, all we have to do is work out how many singleton outcomes we have, and then times it by n factorial. So how many singleton outcomes are in event 1? So how many singleton outcomes, how many outcomes satisfy the condition that 1 is in position 1? So we put 1 there, then how many things can we put here? We can put n minus 1. Then we can put n minus 2 here for each one of those. So it's n minus 1 factorial basically. So the probability of E1 down here is equal to n minus 1 factorial, the number of singletons in there, the number of outcomes in E1 divided by the probability, multiplied by the probability of a single outcome, which is 1 over n factorial. Okay, so that is equal to 1 over n. And that's true for any, because of the beautiful symmetry of this problem. It's the same, probability of E1 is the same as probability of E2 is the same as probability of E3. So that's equal, we can stuff 1 over n into all of those. Right, so we get, sorry, I'm using little n here, which is confusing. I mean big N. Big N. Big N is the number of cards, so clearly this should have been 1 over big N factorial rather than little n. Okay, now we wanted to tackle the probability of EI intersect EJ. Okay, so again, we just need to know how many outcomes are in EI intersect EJ. So how many outcomes are in EI EJ? How many outcomes in EI intersect ej, and then we just need to multiply that by the probability that you're in the probability of a singleton, which is 1 over n big N factorial. Okay, so how many are in there? Well, that would mean that you would have to have the ith one would have to have the ith card in, and the jth one would also have to have the jth card in. So how many things could go in this one? n minus 2. How many things could go in this one? n minus 3, etc. So it's going to be n minus 2 factorial. The number of them is n minus 2 factorial. Therefore, the probability of EI intersection EJ, and just to spell it out, it's equal to n minus 2 factorial times the probability, well, we could write it out even more. We could write it out as the probability of the union of the outcome is an element of EI intersect EJ, and we're unioning up all of the singleton sets containing that. And because these are all disjoint sets, we can write this as the summation x is an element of EI intersect EJ of the probability of that single outcome that event containing the single outcome. Okay, and this is equal to 1 over n big N factorial, because they're all assumed to be equally likely, and the number of them we've got is n minus 2 factorial over n factorial. Okay, time for another piece of paper. Right, so, in this bit here, we therefore stick that the probability of these, the probability of EI intersect DJ is n minus 2 factorial over n factorial. And I just want to, so that we can turn our attention to adding up how many we've got here, I'm just going to say, if we take the probability of EI intersect EJ intersect whatever, however many we need, let's just say k, but I don't necessarily mean that we've just got 3. I mean if we're intersecting arbitrarily many, the probability of that, well, it's going to be the number of these. Well, we're going to fix k of them, therefore we start with n minus k possible ones that could go in the free card play positions, and then we go down. So the probability of that is going to be n minus k factorial divided by n factorial. So I'm just generalizing this result and this result to the and this result here to the arbitrary cases where we've got these intersections. So that now we can just concentrate on these summations. Okay, so now all we need to worry about is how many we're going to get of, for instance, P, EI intersect DJ. Well, it's over I is less than j. So we're asking how many ways are there to select 2 of these events. That's n choose 2. So what we're going to end up with is here we had the n choose 1 effectively times 1 over n. Then here we're going to have the number of possible basically this probability here for any I and any j is equal to n minus 2 factorial over n factorial. But all we're trying to work out now is how many of these are we adding up, and the number we're adding up is how many ways are there of selecting 2, an I and a j from n things, and that's n choose 2. So n choose 2 times n minus 2 factorial rather over n factorial, and then it goes on plus n choose 3, which is the next term in the inclusion-exclusion principle, n choose 3, and then it's going to be n minus 3 factorial over n factorial, and it's going to go on all the way down to minus 1 to the n plus 1, and the probability of all of them intersected is going to be n minus n factorial times n factorial, and then you're going to have to say how many ways are there of choosing n things from n things. So of course there should have been n choose n here as well, n choose n in there, which I've missed out. So obviously those all go because they're all 1. And basically if we write all of this out, if we write out these here, so n choose 1 is going to be n, so that's going to go over n. Then we get n minus 1 over oh right, sorry, no, I should write it out properly, it's going to be easier to cancel it. N choose 2 is n factorial over n minus 2 factorial, and then we've got n minus 2 factorial over n factorial. Then we've got plus n factorial, n choose 3 now, which is n factorial, n minus 3 factorial, 3 factorial, n minus 3 factorial over n. And you can see the pattern. These are all going to cancel, and what we're overall going to get is 1 minus 1 over 2 factorial, plus 1 over 3 factorial, minus 1 over 4 factorial, plus 1 over 5 factorial, all the way down to where are we going to go? Oh no, that's fine, sorry. When I said all of this cancels here, n minus n is 0, so that's 0 factorial, so that bit goes, and n choose n is 1, but the 1 over n factorial remains. So we go all the way down to plus minus 1 to the n plus 1 over n factorial. Now, you can have fun trying to add up this series if you like. Do I know a summation formula for factorials like that? Let's have a little think. How would you actually compute the actual answer to that? Do I know a way of doing that? Delta s delta x is equal to 1 over x factorial. X plus 1 minus 1 minus... No, I don't think I can see an easy way of doing that. Minus 1x... Or maybe I can. Let's have a little look. Let's just look. I'm just as an offside. This isn't really part of the main video. In fact, I'm going to do the main part, and then we'll see if, just out of interest, I want to see whether I can actually find a way of adding that up and getting the exact answer. What you might note, though, is that this is very similar to the Taylor series for e to the x. So the Taylor series of e to the x is 1 plus x squared. Well, this is actually the Maclaurin series for e to the x, but most people call it the Taylor series because, you know, Taylor's theorem. I don't know whether Brooke Taylor actually proved Taylor's theorem. I presume he did. The problem is Taylor's theorem is also a theorem in complex analysis, which again you prove that, you know, any holomorphic function locally is expandable as the Taylor series. But I'm pretty confident that Brooke Taylor did not prove that. So I'm not, but I presume Brooke Taylor must have proven something about the convergence of the Taylor series. Otherwise, why would they all be named after him rather than Maclaurin? I don't know. He must have done more somehow. Plus x to the 4 over 4 factorial, and then it goes on and on and on, for instance. So if it's actually the sum from r is equal to 0, is it? Yes, to infinity of x to the r over r factorial. So the limit of the partial sums. And this converges on the whole real line. And I believe, yes, it does. I think it converges on the whole complex plane, in fact. Okay, so what does it converge on the whole complex plane? E to the x has a... yes, it does converge on the whole complex plane. Right. Okay, at least I hope it does. I'm questioning myself now. E to the x is holomorphic on the whole complex plane. Therefore, yes, it does obey this. It is expandable as this on the whole complex plane. Okay, that's not important at all. Okay, so if we want to get similar to this, well, firstly, we need to put in what? If we put in -1, what are we going to get? We need somehow to get this -1. And you might think, well, this looks kind of like what I saw in, you know, way back when I saw a derivation, not a proof, of Euler's famous identity. You know, you stuck I into it, and things, and you know, that might look how you'd get these -1s in front of the even terms, maybe, but no, you don't. If we stick -1 in here, you get 1 minus 1, because that would end up with loads of imaginary terms, and we don't want that. We'd get plus -1 squared over 2 factorial, so that stays as 1, so all the even terms are going, even power terms are just going to stay as 1. Then we're going to get -1 over 3 factorial, plus 1 over 4 factorial, and then if we take, well, firstly, if we take, we firstly want to get rid of this 1 here at the, well, you see this, we've got two 1s here, we've got a 1 and a -1. We don't want both of them, so firstly we want to, actually no, firstly we want to times this by -1, so -1 of e to the -1, which I'm going to write as -1 over e, so that it doesn't look so confusing, is equal to -1 plus 1 minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial, etc. Dot dot dot. Which is looking very, very similar to what we had before. Okay, so how close are we now? Okay, we just need to add 1 to it, don't we? So 1 minus 1 over e is equal to 1 minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial, etc. onwards. And we would write that as the sum from r is equal to 1 to infinity, so the limit of the partial sums again. I always like to say that to myself so that I know that I'm not just, you know, it isn't just a sum, it's the limit of the partial sums. It's something far more scary. Well, firstly it's negative 1 over r factorial, and now I just need to work out what power I need to raise that to. So the even terms are going to be odd, so it needs to be r plus 1. There we go. That will work. So the limit of that sequence is 1 minus 1 over e. So we can say that the answer to the matching problem, whatever n is, well, the bigger n gets, this gets in a better approximation. But for any matching problem, however many cards you have, the answer is going to be very, very, very close to this, because these terms vanished oh no, actually. Sorry, ignore me. I was getting a bit concerned about the negative signs, but still, the terms get very, very small very, very quickly. And in fact, this is an absolutely convergent sequence. Because, you know, if you put the absolute value in front of it's an absolutely convergent series, rather. If you put the absolute value in front of all these terms, you'll get it converges to e. So it is absolutely convergent, and therefore this series is convergent with the alternating signs. And the terms get so small after a while that it gets so very, very, very close to 1 minus 1 over e. But the bigger your n is, the more close it is to minus 1 over e. But even with, you know, n is equal to 10 or something, you're so close to this that it's, yeah. So that is effectively your answer to the matching problem. What I want to now do is see if we can actually add up this finite sequence, this finite sum here. Okay, so let's try and employ calculus of finite differences. So we want to find a function where the discrete derivative, the finite difference, or the finite derivative, whatever you want to call it, is going to be equal to. So the derivative, the finite derivative of s, the finite derivative of s of x is going to needs to be equal to negative 1. That's the problem. This alternating series thing. Is there any clever way? Let's just have a little play. 1 over x factorial, if we take 1 over x plus 1 factorial and we subtract 1 over x factorial, so that's the difference where we're letting the difference equal 1. So we might put a 1 down there. What's that going to equal? Well, we can factor out the 1 over x factorial, and then we've got 1 over x plus 1 minus 1. So basically, let me just explain what I'm trying to do. I'm trying to... what are we taking this sum from? Okay, basically what I'm trying to do is define... if you imagine the integers sitting here, 3, 4, 5, etc. To each one of those, I can ascribe one of these terms. So I can, you know, that at 1 it will be 1, then here it will be minus 1/2, well, it should be there. Up here it will be 1 over 3 factorial, which is 1/6 something, you know. So I'm ascribing each of these numbers, so just a function which is mapping me to the terms of the series. And I want a cumulative function, s of x, which actually isn't defined on the bits in between, but just needs to have the correct values on the integers, such that when I take the difference between this one and this one, it's equal to this bit here. Basically, this is almost like the finite derivative of it. Okay, so you might ask, why am I not dividing by delta x? Well, I am, because delta x is just 1, so dividing by it has no effect. Okay, so that's what I'm trying to do. I'm trying to calculate the derivative of this function to see whether I can get any intuition onto whether I can find a function whose finite derivative is minus 1 to the minus 1 to the x plus 1 divided by x factorial. Okay, so this has got the x factorial nicely. This is 1 minus x plus 1 over x plus 1 is minus x, and then you'll get the minus 1, so you'll get minus x over x plus 1. That's not looking so great, is it? No, not great at all. So you could cancel the x from the x factorial, but you just get something hideous. Finite sums. Is there anything clever I can see of how you could calculate that exactly? I can multiply them all by... I can multiply it all by -1, but what's the point of that? Multiply... No, I don't think there is any clever way that I can instantly see of doing that. Well, never mind. I had a go. I hope you have understood this video on the matching problem. All that I was trying to do at the end was actually find you an actual answer to what is that sum, rather than just an approximation. The answer is approximately equal to 1 minus 1 over e, and the bigger you make n, the more close it gets to 1 minus 1 over e. But I will keep thinking about that problem, and I advise you do as well, and see if you can come up with an answer.